Now that I have properly and completely traumatized you with the quiz question, I want to bring into focus why I gave you that quiz question and how we're going to start applying that concept to other things. What I have here on my screen, it's going to be a positive and a negative charge, and they are equally equidistant apart, which I guess wouldn't be hard because you're going to draw a midpoint, so they're always going to be. But this is what we call a dipole. It has both a positive and a negative end. I want to come up with an expression for defining the electric field created by a dipole. And so we're going to use the same process we did in the quiz question. This would be akin to the two charges that were further away from the point that we were interested in. Because you'll remember the top right corner was the negative charge and the top or lower left corner was the positive charge. So the question I kept asking everybody is, okay, what's going to happen to our test probe charge? How is it going to interact with the electric field from this positive charge in the bottom? And what we say is, okay, the electric field emanates out from a positive charge. So my positive test probe charge then would be repulsed away, something like that. So that's the direction of the electric field at that point because of the positive charge. Now I want to do the same thing with the negative charge. This one is going to be attracted to, let's see if I can't do this, attracted to the negative. I'm not making it a vector, so it actually maybe goes through. Nope. Let's try this again. Let's start from the charge. I'll draw in the arrowhead after. There we go. And there was a reason I'm trying to be a little more precise with this than I normally am. So the field is going into the negative charge. So I'm going to have this vector coming up here from the positive and the vector going up relative to the negative. And I've defined the distance separating the two charges as s. So the one thing I was having everybody do as we worked through these then is, now let's focus on these two resultant vectors, these guys here. And I can remind myself that in general I define an electric field in terms of coulombs. My electrostatic constant K, Q is the charge creating the field divided by my distance away. So one of the first things we were doing then is, so how do we define this distance away? And we need to do that in terms of this hypotenuse, as just a straight line distance away. So I have a right triangle, and I know that this overall distance between the two is s. So that means if I take the origin as like my spot to make my right triangle off of, I'm going to have two sides that are s over 2. S over 2. I haven't labeled where this dot is, but this is just an xy axis, isn't it? Where that's my y and this is my x. So let's just call this a distance x away. The peanut gallery is not cooperating right now. We're going to call that a distance x away. Ignore him. Then by Pythagorean, the distance here is going to be s squared over 4 plus, now my distance here is that distance x plus x squared. So I know that distance, and I also know then that that distance is going to be my r. So the square root of s squared over 4 plus x squared. So the next thing I want to do then is break this into x and y components and see if by symmetry anything is going to cancel out. And I look at this and I can see if I had drawn complete vectors that were nice and even, it would be more apparent. But if they're equidistant away and the same magnitude of charge, let's see, I'm going to have an x vector coming out like this on that side, and then an x vector going out like this on that side. Same distance, same charge, so the component in the x direction is going to cancel. So that's nice. That tells me the only thing I am worried about for both of these is my y component. There's a y component there, and there's a y component there. Whoops, didn't draw my arrow. That's what I want. And let's define that in terms of our trig. Now, just a reminder, while I don't know the length of my electric field vectors, I've intentionally drawn them out just to make it easier to see the angles in the work I'm doing, but that's not their actual length. What is true is the proportions of the triangle from the geometry, so the position, is going to create a same angle. So I'm going to have a same angle here as I do here. Do a different color. I'm going to have the same angle here as I do here. So I can use my trig functions in terms of the sides to figure out the y component of this thing that I've made. So what is my y? Well, this side is x, and the hypotenuse that we've defined is going to be the same for both sides. So this square root of s squared over 4 plus x squared. So that's the same for both. So I can come over here and say, okay, so sine theta equals opposite my s over 2 over the hypotenuse, over the square root of s squared divided by 4 plus x squared. Cool. I know I'm going to have two of them, so let's just kind of focus on what's going to happen to just one of those y vectors, because we're just going to multiply it by 2 in the end. So my e and the y then, it's going to be, let's see, my kq divided by my r squared, so that's this piece squared, which is going to give me just my s squared divided by 4 plus x squared. Now times the y component. So I'm taking, remember this thing here equals this thing. If I put the angle in with my sine theta, I'm going to get the exact same numerical value I would get out from what's on the right. So I can use that expression. So s over 2 divided by, and I'm going to do this with exponents as fractions instead of the square root. I'm going to show you why in a second. To the 1/2. And this is going to be y hat. Both of my vectors are going up. I'm above axes, so I'm going to call this thing positive. Cool. Now what I can look at is I can look at these two expressions on the bottom, and they are the same, but this one has the equivalent of a 2 over 2 exponents, just raised to the 1, right? So what I can do is combine these things. So 2 or 1 plus 1/2 is going to give me 3/2. So let's rewrite that. So I'll have kq s over 2 divided by s squared divided by 4 plus x squared to the 3/2. And this is y hat. Okay, so that's my e and the y. Let's go ahead and simplify this. There's 2 y's. So I'm going to multiply this by 2, which is going to make that go away, and we can pretty this up finally by saying e and the y equals kq s divided by s squared divided by 4 plus x squared to the 3/2 in the y hat. Sweet. Now what do I do? Well, I think I can simplify this. Let's take this into a real life thing. This is a dipole, so you can think of it as two atoms of opposite charges hanging out together. And that means that the distance separating them, the bond length, is teeny, teeny, tiny. And if I look at my distance over here at my x, chances are that distance is much, much greater than this distance s. So if x is much, much greater than s, the distance separating my two dipoles, then I can rewrite this expression. When I look at the addition, I say, okay, so x is a lot greater than s, so that means that s is going to be like 5 would be the x, 0.00000004. Well, that 0.00004 is not significant. So then I can rewrite that and say that e to the y for s is much greater than s is kq s divided by x squared to the 3/2 in the y hat. Then I can look at that. Well, the x squared to the 3/2, that's going to simplify down. My 2's are going to cancel out. And this gives me finally the expression you find in your book for a dipole. KQ, S, so the bond length distance between the two, times x cubed, the distance away. And there you have it. So we have now derived, using something that you've been practicing on your quiz, an expression for a dipole. So one of your homework questions has a charge interacting with a dipole. This is the electric field for the dipole. If I wanted to know the force, then let's rewrite this. Instead of e to the y, we'll call it e to the p for dipole. Why they choose p for dipole, I don't know. So force then is going to be some external charge, some other q interacting with the electric field of the dipole. So if we are at a distance x much greater than s, I would have, then the force would be whatever this external charge is that's interacting times this dipole piece, kq s, let's call this 1 and 2 s over x cubed. And you'll see this further simplified down, where this q and this s is going to be what we define as the dipole moment. So that's where that p is going to come into. So you'll have q2, kq2 times p, the dipole moment, which is just this q1 times the distance separated, divided by x cubed. And there you have it.